Today I'm going to be introducing you to implicit differentiation. But before I begin, some tips and tricks for watching this video. This could be a long one, and it gets a little bit complicated at times. So number one, try not to get bogged down in the algebra. The algebra is very important, but I don't want it to get in the way of your understanding of the overall calculus concepts. I'll go through the algebra quickly, partly so that the video doesn't turn into like a 3-hour video, also because the purpose of this video is not to reteach the algebra. So that means you need to pause the video if you feel like I'm going too quickly. Number three, perhaps watch the video twice. Maybe once, just watch it. Get an overall impression of the calculus concepts, and then a second time to make sure you really understand all the calculations. Today we're answering the question, how can we take derivatives of a function that can't be written explicitly in terms of x? Up to this point, we've been differentiating functions that are solved for y explicitly. That is, functions that can be written as a y equals with all of the x stuff on the other side. Now we want to consider functions that can't be solved for y alone. First, some basic facts to consider related to implicit differentiation. These may not make sense right away, but go back and reread them after the lesson, and then I think they'll make sense to you. Realize that differentiation is taking place with respect to x. When you differentiate terms involving x alone, you just differentiate as usual. But when you differentiate terms involving y, you have to apply the chain rule of sorts. This says we're taking the derivative of x with respect to x. And the derivative of x is 1. We've learned that before. Now, what happens if we take the derivative of y, but still with respect to x? The derivative of that is dy dx. And I suppose you could think about it like, if I were to just kind of put this x on top, multiply it together like they were all a bunch of variables, I'd get dx over dx, wouldn't I? And that's 1. But here the y pops up, it's just dy dx. This is a very important part of implicit differentiation. So the steps for implicit differentiation, number 1, differentiate both sides with respect to x. Remember to multiply dy dx each time you differentiate an expression containing y. That's the chain rule. Isolate dy dx by getting all the dy dx terms onto one side of the equation and all the other terms on the other side. This is the algebra heavy part. Factor out dy dx and solve for dy dx. Here we go. Find dy dx for xy plus y equals 8 at 3, 2. First, let's get a feel for the equation we're working with. We've got two terms on the left. The first is going to require the product rule. And then we have a constant on the right. So we'll start with the left side. And because we're going to use the product rule, I just put some parentheses in there. So if x is the first term, y is the second term, then the product rule says take the derivative of the first, so the derivative of x is 1, times the second, plus the derivative of the second. Now we're taking the derivative of y, and that's what I told you earlier. The derivative with respect to x of y is dy dx. So back here, we've got the derivative of the first times the second plus the derivative of the second, that's dy dx, times the first. Now we need to differentiate this plus y. So that's going to be plus the derivative of y, which again is dy dx. And then what's the derivative of 8? That's a constant. So the derivative of a constant is 0. This is the calculus part. Next, we're going to do all the very heavy algebra stuff, so buckle up. First thing we're going to do, subtract y from both sides because I want to get all the not dy dx stuff on one side and all the dy dx stuff on the other. Next, I will factor out a dy dx because my goal is to get dy dx completely by itself. So to isolate dy dx now, I just divide both sides by x plus 1. Next is to evaluate it at the given point, 3, 2. So now we just plug in what we know. But there's a special way to write this. So this says dy dx, and then this up and down line is like our evaluation line. So this would read dy dx evaluated at 3, 2, or just dy dx at 3, 2 equals, and now just plug in your x and y values. So 2 over 3 plus 1, negative in front, you get negative 1/2. We did it. Time for another one. So we have a single term followed by 3xy. So we're going to need the product rule for that one, 3x and y. Those are two functions being multiplied together. And then a single term here and a constant at the end. So we'll start with the derivative of x, which is 1, plus. Now because we have to use the product rule, I'm going to put some parentheses in there. 3x is the first term, so derivative of 3x is 3 times the second, plus derivative of the second term is y, derivative of y is dy dx, times the first term. And then we'll subtract. Now, when we take the derivative of 2y squared, the 2 is going to come forward, okay, so we get 4y. Then, because we've got this y involved, this is when the chain rule comes in. So y sort of becomes this inside function. So we have to take the derivative of the inside function, dy dx. So anytime you have a term with y in it, just follow it up with a dy dx. And then 2 is a constant, so this equals 0. That's the calculus part. Now comes the algebra. So these are my non-dy dx-y things. So we'll subtract those from both sides. Then we can factor out a dy dx. And then isolate dy dx by dividing both sides by 3x minus 4y. And now we can evaluate it. So dy dx evaluated at 1, 1 is negative 1 minus 3 times 1 over 3 minus 4, which is 4. Next one, find y prime for y e to the x equals 3 pi. Again, let's get to know the equation in front of us. On the left, we have two functions being multiplied together, so we'll have the product rule. And on the right is 3 pi. Pi is a number, so 3 times pi is still just a constant. Keep that in mind. So for the product rule on the left, we'll have the derivative of the first, dy dx, times the second, e to the x, plus derivative of the second. The derivative of e to the x is still e to the x, times the first. And the derivative of 3 pi is 0. Now we'll get this guy over to the other side, and then we can cross out those e to the x's, and we're left with dy dx equals negative y. Shall we try one with some trig? Step 1, get to know your equation. So we have the cosine of something, and that of something is two functions being multiplied together. So just on the left, you have a composite function, two functions being multiplied together. So you're going to need the chain rule and the product rule. That'll be fun. And then the right side looks pretty straightforward. So first, the chain rule. Cosine is the outside function. So the derivative of cosine is negative sine. Keep the inside the same. And now we'll take the derivative of the inside using the product rule. Derivative of the first times the second plus derivative of the second times the first. That's the left side. And that equals, okay, derivative of x is 1. Derivative of 3y is 3 dx dy. So that's the end of the calculus part. Now we get into the heavy algebra stuff, and our first step is going to be to distribute this negative sign xy through my brackets. Wow, it gets complicated fast, doesn't it? But again, our goal is to isolate dy dx. So we'll get all the dy dx stuff on one side, anything that's not dy dx on the other side. Then factor the dy dx and divide. Now we're going to do a natural log function. We can do this problem two ways. I see a composite function here, the natural log of something, and that something is two functions being multiplied together. So I could use the chain rule and the product rule, or another option when you see logarithmic functions is to see if you can rewrite it using the log rules. So that ln x times y, we can rewrite that as ln x plus ln y. This might make it a little bit easier. If you decide to use the product rule and the chain rule, you'll get to the same answer. So the derivative of ln of x is 1 over x. Derivative of ln of y is 1 over y. But because y is involved, we're following it up with the dy dx. And then the derivative of sine x is cosine x. Again, that's the calculus. Here comes the algebra. So get this 1 over x to the other side. Multiply both sides by y, and you're done. Life isn't complete in calculus until we've written the equation of a tangent line. So this says, given x squared minus xy plus y squared equals 7, find the equation of the tangent line and the normal line at x equals negative 1, 2. Anytime we're trying to find the equation of a tangent line, we need two things. We need a point and we need a slope. They've given us the point. Now we'll take the derivative to find the slope. So here's our function here. We'll start with x squared. Derivative of x squared is 2x. Now xy is two functions being multiplied together, so we need to use the product rule. Derivative of the first times the second, plus derivative of the second, derivative of y is dy dx, times the first, plus, now when we take the derivative of y squared, 2 comes forward, drop the power by 1, so that's 2y. And then because we've got y involved, we're going to tack on that dy dx. And then the derivative of 7 is 0. Okay, now don't forget this negative applies to the negative y and the negative dy dx times x. So with that, we'll get all the dy dx-y stuff on one side. I put it on the right side this time. And all the other stuff on the left. Factor out dy dx and divide both sides by x minus 2y. So that's the derivative. That means at any point on our graph, we can find the slope of the tangent line. So let's do it. We want the slope of the tangent line specifically at negative 1, 2. So we'll evaluate our derivative at that point. That gives us a slope of 4/5. Now we've got the slope, we've got the point, and pop that into point slope form for the tangent line. It also wants the equation of the normal line. Do you remember what that is? That's just the perpendicular to the tangent. So instead of 4/5, the slope is going to be -5/4. But everything else stays the same. You will be excited to know that you can take the derivative of a derivative. So we've been hanging out here in this first derivative. And in this top line, y prime, f prime of x, dy dx, derivative of a function, those all mean the same thing. If I have a function y and I take the first derivative, I get y prime. If I take the derivative of that, I get y prime prime. If I take the derivative of that, I get y prime prime prime. And then they were like, yeah, we can't just keep writing little apostrophes, so then we're just going to move to numbers. So here's the first derivative, second derivative, third derivative, fourth derivative. With that in mind, let's try it. Find f double prime. That's the second derivative given this function here. 3/2 x cubed plus 5x squared minus 6x plus 1. So you can take the derivative of this regular old polynomial by using the general power rule. And the first derivative is 9/2 x squared plus 10x minus 6. To find the second derivative, you just pretend that that's a function in and of itself, which it is, and take the derivative of it. So now we have found f double prime of x, or the second derivative of f. Hey, we can find a fifth derivative. That'll be fun. So notice what power we're working with. Our leading power is 4, an exponent of 4. So let's see what happens when we take the fifth derivative of this polynomial. Pay special attention, if you would please, to the leading term's power. First derivative, -12x cubed plus 21x squared minus 10. Okay, so the 4 has gone to a 3. Take the derivative of that one. Our second derivative is -36x squared plus 42x. 3 drops down to a 2. Take the derivative of that. You get -72x plus 42. Take the derivative of that, and you get -72. I guess you could think about it as x to the 0, right? And the derivative of that is 0. So when you're working with just a polynomial and you start taking multiple derivatives, eventually they'll disappear. They'll disappear at the leading power plus 1. Holy cow! 32nd derivative of sine of x. You ready for this? Whew. Okay, first derivative, cosine x. Second derivative, negative sine x. Derivative of negative sine x is negative cosine x. Derivative of negative cosine x is sine x. Oh, hey, look at this. That is the original function, which means any multiple of 4 will give us back the original function. That's a shortcut. So, since 32 is 4 times 8, it's a multiple of 4, then the 32nd derivative of sine of x is sine of x. Let's try the 867th derivative of cosine of x. Let's just start, see what happens. First derivative is negative sine x. Second derivative is negative cosine x. Third derivative is positive sine x. Fourth derivative is cosine x. Again, we are back to our original function. So any multiple of 4 gives us the original function again. So 867, if you divide that by 4, it doesn't go in evenly. it goes in 216 times with a remainder of 3. So that means the 867th derivative of cosine x is the same as the third derivative, which is sine x. Why are we going through all these higher order derivatives? Because we can do the same thing with implicit differentiation. We can take multiple derivatives, but it's a little bit more complicated. So be sure to solve for dy dx before finding the second derivative or higher. That's going to be important. Fully find the first derivative first. Then subsequent derivatives, this dy dx term is going to keep showing up. So for each of these terms, you can make a substitution to be able to put your final derivative just in terms of x and y. I'll show you what that looks like. All right, we're going to find the second derivative of cosine y equals x. Cosine y is essentially a composite function. So we'll take the derivative of the outside. The derivative of cosine is negative sine. Keep the inside the same. And then the derivative of y is dy dx. And then the other side, derivative of x is 1. Now we solve for dy dx. So dy dx equals 1 over negative sine y. We need to take another derivative here, and I don't really feel like using the quotient rule, so I'm going to rewrite this as negative sine y to the negative 1. I have another composite function here. Got this outside, something to the negative 1, and then the inside of sine y, and then the inside of just y. So taking the derivative of the outside function, the negative 1 will come forward. You get sine y to the negative 2. Now the derivative of sine y is cosine y, keeping that y the same. And then the derivative of y is dy dx. So like I said, this dy dx term keeps popping up. But the cool thing is, we actually know what dy dx equals. dy dx equals negative sine y to the negative 1. So we can substitute that back in. And if we clean it up a bit, there we have our second derivative, negative cosine y over sine y cubed. Now as a bonus, there's one more substitution we can do. Anyone see it? Look at this, cosine y. What was our original function? Cosine y equals x. Haha, let's pop that back in too. All right, we're done with that one. Find the points at which the graph of x squared plus xy plus y squared equals 27 has either a horizontal or vertical tangent line. Wow. So if we're looking for horizontal or vertical tangent lines, we need to start by finding slopes. So pause the video and go ahead and use implicit differentiation on this function right here. That's what I got. 2x plus y plus x dy dx plus 2y dy dx equals 0. Now we'll take that 2x minus y, pop that over to the other side, factor out a dy dx, isolate dy dx. And there we have our slope. Once we have our slope, we can figure out where a horizontal tangent line would be. Now, a horizontal tangent line looks like that. It has a slope of 0. So in order to get this fraction to equal 0, we actually only care about the top equaling 0, because 0 divided by anything is just 0. So we'll take the top and set it equal to 0. Well, now what do we do? If we solve for one of the variables, say y, you get y equals negative 2x. So anywhere that y is negative 2x will have a horizontal tangent line. But where is that? Thankfully, we have two variables and we have two equations. we have a system of equations. So we can take this y equals 2x and plug that into the original equation. And we'll go ahead and simplify that to get x equals plus or minus 3. So there we go. There are our horizontal tangent lines. We're not done yet though, because it wanted the vertical tangent line also. So to find the vertical tangent line, what do? That would be when the bottom equals 0, because you can't have 0 on the bottom of a fraction. So same process as we did before. We're going to solve for y. We get y equals negative 1/2 x. Anytime y equals negative 1/2 x, you get a vertical tangent line. In order to find where those places are, we'll go ahead and substitute y into the original equation to solve for x. It looks nasty. And remember, this is the algebra heavy part. So either pause the video or just enjoy the math for a second. Combine like terms, solve for x, and anytime x is plus or minus 6, we have a vertical tangent line. That was a lot of information today. A lot of new information, a little bit complicated. So don't worry if you're still feeling a little bit confused. Practice makes perfect. Practice, 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 and you'll get it. And again, just run the video back again. Watch it again. Enjoy the math. See you next time.